All right, this is Honors Algebra 2 Pre-Calculus. We're doing 7.2 in Algebra 2, which is end behavior. So this is our second video. All right, so let's talk about the end behavior of polynomials. So end behavior describes what's happening to the curve for very large positive or negative values of x, meaning as x approaches a positive or negative infinity, so all the way to the right or all the way to the left, depending on which way you're looking at it. The end behavior of a polynomial depends on exactly two things. Is the degree of the polynomial even or odd? And is the leading coefficient positive or negative? So essentially there are only four scenarios for how a polynomial behaves at its ends. So let's go ahead and walk through what the four look like. So if a polynomial has an even degree, then both ends go in the same direction. So specifically, if a polynomial has an even degree and a positive leading coefficient, then what happens is both ends go up. They look like this, right? And there might be a bunch of stuff in the middle. So in the case of just an x squared, there's not a bunch of stuff in the middle. It's just a parabola, but it could do some stuff in the middle. It won't matter. All we care about is that both ends go up, right? A negative leading coefficient of an x squared, or any polynomial function with an even degree, both ends are going to go down, right? And so again, there could be stuff that happens in the middle. We don't really care because it's end behavior, so we only care that both ends go down. Again, the easiest way to think about this is the simplest possible example of an even degree with a positive coefficient is an x squared, right? X squared just looks like this, right? Yay. And a negative x squared, which just looks like this. So if you're trying to picture which option it is, you can picture it that way. An odd degree, so the easiest example is an x cubed and a negative x cubed. Well, if a function has an odd degree, so if you picture a positive x cubed, it looks like this, and if you picture a negative x cubed, it looks like this, and that pretty much encapsulates everything you need to know about this. So a positive leading coefficient and an odd degree polynomial is going to have the left end down and the right end up, and it doesn't really matter what happens in the middle because it's end behavior, so we only care about the two ends. And the same thing's going to be true in the other direction. Again, we don't really care about the squiggles that happen in the middle because we're talking about the end behavior of a function. The mathy way to write these and you'll learn a lot more about limits when we get to calculus, but the mathy way to write this is that the limit as x approaches negative infinity. So what this means is all the way left, right? So all the way left, because x is approaching negative infinity, the y value is a positive infinity. So as you go all the way to the left, you're going up. This one says all the way right. All the way right. Right, as your x values approach a positive infinity all the way right, your y values also approach an infinity. And you can see that that's the mathy way to write all of these. And you don't have to use that mathy notation yet, but certainly when we get to calculus, it's going to come into play a bit. So let's go ahead and do a couple of end behavior problems. All right, so remember that when we're describing end behavior, all we really need is the degree of the function and the sign of the leading coefficient. So in E3A, x cubed is the largest degree. So what I'm looking at is I'm looking at a negative leading coefficient. I'm looking at an odd degree. So I'm looking at a function that looks like this. And it could do all sorts of crazy stuff in the middle, but I don't care. I only care about the two ends, right? So the left end is up. The right end is down, right? You'll see this written a bunch of different ways. Sometimes you'll see it rising to the left, falling to the right. That's one way to say it. So you could also see this as rising to the left, falling to the right. That's one way you could see it. So you could also see it like this. You could also see the very mathy version that says the limit as x approaches negative infinity, which is a fancy way of saying that you're going to the left, right? This is a fancy way of saying left, as the x's go to negative infinity, is a positive infinity. That's saying the y's go to positive infinity. The limit as x approaches infinity of p of x is negative infinity. That's saying as you go all the way to the right, your y value is negative infinity. That's another way to write it. I don't care. All of those are the same thing. I think this one's the easiest. They all mean the same thing. We're not really going to address limits in this class. We're going to address limits more when we get to calculus, right? So this is a way to think about this in calculus, but it doesn't hurt to introduce it here. When we do E3B, the trick here is that this is not in standard form, right? So this is the biggest power, and it might help you to rewrite this in standard form so you can see it, right? It's a negative x to the fourth plus an x cubed plus a 3x squared minus an x plus a 3. This is the piece that matters, right? So we have a negative leading coefficient. We have an even degree. So this is going to look something like this. And again, we don't really care what happens in the middle. We just care about the two ends, right? So the easiest way to write this is both ends down, right? You could also write this as falling. That says failing over there. Come on, brain. As falling to the left and the right, right? Or like falling in both directions. If you wanted to write this in a really mathy way, you'd say the limit as x approaches negative infinity of q of x is a negative infinity, and the limit as x approaches a positive infinity of q of x is also a negative infinity, right? This is saying as you go all the way left, going down forever. As you go all the way right, going down forever. So that's another way to write it. But again, I would pick this way. It's the easiest. All right, so let's go ahead and try a P3 that's the same idea. Again, the trick is to identify what the leading coefficient is, right? So you don't have to write this in standard form. So here's the leading term, right? So we have a positive leading coefficient, right? And we have an odd degree, right? Because it's an x cubed. So it's going to look like this. And if you know that, right, all you really care about is that this is left end down, right end up. And again, you can pick any number of other ways to write that, but I would suggest that's the easiest. If we do the second one, right, I look through all these and realize that my highest power is the x to the fourth. So this is a positive leading coefficient. It's an even degree. So this is basically going to behave like an x squared, right? It's going to look like this. Both ends are going to go up. Both ends up. And that's it. All right, so two quick final problems in this video, and these actually aren't about end behavior. This is a little bit of curve fitting. So sometimes we use polynomials to model real-world functions, right? So here's an example of a bunch of data, right? So this is a bunch of data from 1960 to 1994 that indicates an increase and decrease in the number of graduates starting in 1960. So you're asked to use a Quartic regression model, and that's what we're going to do in an example. Now you'll notice that although there's a ton of data points, they picked a handful of data points for you to use for a Quartic regression. So let's go ahead and walk through that. So using those chosen data points, we're going to go ahead and find a Quartic model. So the way we do that, just to review, we go to Stat, right? We go to Edit, and then there's probably stuff in my lists, right? It's very likely that there's some stuff in my lists, right? Oh, my bad. Stat, Edit. Okay, there's stuff in my list right now, so I'm going to go up to the list and I'm going to hit Clear. I don't want to hit Delete because I don't want to delete the list. I want to clear the list out. So I'm going to go up to my list 2 and clear it. I don't want to hit Delete. I want to hit Clear. All right, so when I put in my x values, I'm just going to go ahead and put them in order. So I have a 10 and an 18 and a 30 and a 41 and a 44. And we'll go back and double check that these are right when we're done. Then when I put in my y values into my L2, right, I'm going to put a 1679, a 2606, 3089, 2276, and 2517, and hit enter. Double check that they line up. Double check that all of the numbers are correct. Cool. So I'm going to quit out of this, so second quit. So when I go back to Stat, I'm now going to pick Calc, right? And I was told I want a Quartic regression. Well, that means go to the one that says Quart Reg. And the default lists will be L1 as your X and L2 as your Y anyway, unless you use different lists. So I would recommend using them if you can. Let's go ahead and take a quick screenshot of this. So I did a Quartic regression. Now, an interesting option, right? So if we go back for a second, I can actually go back. So let's go back to Calc, or to Stat and Calc. I can make my life slightly easier on most of these calculators if I store this list, or if I store this equation rather. If I go to vars and over to yvars, I'm going to store this in y1. And what's going to happen is if I do this, so go ahead and hit calculate again, right? Now when I go to y, look, it put that in there for me, which is so convenient. So let me just screenshot that so it's already in there. Okay. So look, that's in my y1 for me, which is awesome because now I can use it. So when I ask to find the quadratic regression, I'm going to write an approximate version of it for A, right? So for A, I'm going to write that my y is approximately, and then I'm going to just use rounded numbers, right? So I'm going to use 0.019 x to the fourth minus 1.93, either 8 or 9, depending on if you round or truncate. So again, we go to 3 places. So 3 places, 3 places, 3 places, 3 places, 3 places, right? X cubed plus 63.670x squared minus 723.743x plus 4,296.301. Okay, so that's my answer to A. But for B, I can go ahead and use this because for B, I can just go ahead and plug into my calculator. So you use your Quartic Regression model to estimate the number of high school graduates in 1970. All right. Well, when we do this, 1960, right? 1960 was year 0, I believe. Let's go back up and look at our data. Oh, I lied. 1960 wasn't year 0. My bad. The 1679 was 10. 1950 was year 0, right? So if we go up here, we use this as the point 10, comma 1679, right? So 1970 would be year 20, right? So 1970 is year 20, right? So what they want me to do is they want me to evaluate this, right? So for B, they want me to do y1 of 20. Well, the easiest way to do that on your calculator, right? There's a couple different options. You could go to table set, right? So you could go to table set. You could just start your table at 20, right? And then if I go to table and scroll over, there's my answer, right? So my y of 20 is approximately 2850.389. Students, right? It's not in thousands of students. Let's see, how did we measure it? Number of students who graduated from high school in the United States. It is, yeah, it is graduates in thousands. So thousands of students. Okay, so that's the answer we got from our regression model. Then if we go back and look at this table, right, we have a value in 1970. In 1970, it's 2757. So according to the table, it was 2757 thousands of students, and that's not that far off. So again, the big trick here is that when you're told what model to use, if you're told Quartic regression, there's a lot less thought to it. If you're told to use a cubic regression, again, you're just using the one that you're given. If you're told to use to choose a regression, right? So let's quit out of here for a sec. If we're told to choose what regression we want, so let's just go ahead and do the Quartic regression again. If you're asked to choose the regression, you can gauge how good the regression is based on how good this r-squared value is. Now this one's a 1, which means that this is a perfect model. Not everything's going to be a perfect model. So let's say I had chosen to do a different model. Let's say I wasn't doing a quartic. Let's say I chose a cubic, right? Notice that r-squared is not quite as good as the one that I had for the quartic, right? So see how r-squared's not a 1. The closer you are to 1, the better the match. So the reason I mention this is that whatever set of data you're given, right, certain sets of data match certain things better. There's a lot of different kinds of regressions, right? So if you look, there's linear regressions if something has a best fit line, quadratic, cubic, quartic, but there's also others, right? There's a natural log regression, there's an exponential regression, there's a power regression, there's logistic, there's sine and cosine type regressions, right? So the reason I mention that is that if you were someone who was actually working in statistical data, you would have to make choices about which model best fits your data. If you were someone working in the weather, for instance, right? Weather is not something where we have 100% certainty. We use models to predict the weather. Well, the way those models are chosen are by what seems to be the best fit for the data that we have at hand, and as the data changes, the model changes. So that's just sort of the way this works, and it's worth noting. So let's go ahead and do a P4. So in P4, you're given some data, and you're just asked to do a quadratic regression, right? So here, there's not a lot to it. I'm just going to go to my edit, I'm going to go to my lists. And again, the easiest way to get rid of it, you could individually delete the terms, but the easiest plan is to go up to the top of the list and hit clear. So my x coordinates are 2, 5, 6, 9, and 11, right? And then my y coordinates are 4, 16, 11, 14, and 9. Oh, my bad. All right, and then we quit out of here. I'm going to go to Stat and Calc, and I want to pick Quartic Regression, which was 7. And again, the default settings are to use L1 and L2. So there's my Quartic Regression, right? Interesting side note, and we haven't actually addressed it here, but the same way that you were able to use matrices to find an exact fit for a quadratic, right, with ax squared plus bx plus c, you could do that with Quartic if you had sufficient points, right? Since there are 5 coefficients, a, b, c, d, e, you would need 5 unique points, 1, 2, 3, 4, 5. So you could actually do this not as a regression, but just straight up you could find this exact quartic model. So it's worth noting that if you have 5 points, you can find a unique quartic model that will fit those 5 points. But here I was just asked to find a quartic, so I'm going to do that, and I'm going to get negative 0.100 x to the 4th plus 2.741 or 2, depending if you're trying to truncate, x cubed, minus 26.158 or 9, depending if you round or truncate. Again, you shouldn't write both answers. You should just pick one, but I need to have both as your teacher so that I know that they're both correct if you put different answers, right? So that's with the x. And then lastly, 112.785 or 6. So again, you don't need those parentheses underneath. You just pick either you round or you truncate. I do both because as your teacher, I need to know which answers are possibly correct. So if, just as a side note, if you had chosen to do so, you could do this with matrices, right? Like you could do, we've seen this before, and this is not how I would recommend doing it, but you certainly could. So plus dx plus e, you could take each one of these points, right? And you could say y equals, so this would be a times 16 because the x to the 4th, plus b times 8, plus c times 4, plus d times 2, plus e, right? And you could do that with each row, right? You could take 2, 4, and what would end up happening is you'd end up with a 5 by 5 matrix, right? So you could do this, and then you could do a inverse times b. I'm not going to recommend it, but you certainly could. So you can see if you did 5, 16, right, you'd get 16 equals a times 625 plus b times 125 plus c times 25 plus d times 5 plus e. And you could make, you'd essentially get a 5 by 5 matrix, right? And that would, and then your variables a, b, c, d, and e, and it would equal your constant, your 5 by 1. Right, and it would be all the constants. So you certainly don't have to do that. I just wanted to show that it is a possibility if you wanted based on prior information that we've learned. And that is it for 7.2.